All right. So last time I mentioned error estimate for alternating series, and we did some examples of Maclaurin series, right? The error estimate was as follows. If you have an alternating series which satisfies the conditions of the alternating series test, suppose S is the sum of all the terms and Sn is the nth partial sum. So if I take this as an approximation for the whole sum, the error is S minus Sn in absolute value. And we showed that this error is at most the n minus first term of the series. Okay. Now I'll continue with some other examples of Maclaurin series. Okay, so examples. Find the Maclaurin series for the functions sine x and cosine x. Determine the intervals of convergence of this series. Okay, so first one is sine x. Since I said Maclaurin series, it means c is equal to 0. Okay, so I need to compute the derivatives of sine x at c equals 0. Well, f prime is just cosine x. F double prime is minus sine x. F triple prime is minus cosine x. Fourth derivative is again sine x, and then it will just keep doing this, right? So it will start from sine and then cosine minus cosine sine and so on. It will go like this. So in particular f of c, which is f of 0, is just 0. F prime 0, so this will be my a0. F prime 0 is just 1. This is my a1. F double prime, no. What was the formula? An was nth derivative of f at c divided by n factorial, right? We have to be careful. Okay, so a0 is 0th derivative, so it is just f of 0 divided by 0 factorial. F of 0 is just 0 because it is sine 0 divided by 1, which is 0. A1 is f prime 0 divided by 1 factorial. It is cosine 0 divided by 1, which is just 1. A2 is second derivative of f at 0 divided by 2 factorial. Second derivative is minus sine 0 divided by 2 factorial, which is 2. So this is again 0. A3 is third derivative of f at 0 divided by 3 factorial. This is minus cosine 0 divided by 3 factorial. So it is just minus 1 over 3 factorial. Let me write it this way. And then A4 is fourth derivative of f at 0 divided by 4 factorial. Fourth derivative is just sine x again. So it is sine 0 divided by 4 factorial, which is 0. So the Taylor series or Maclaurin series for sine x, hence the Maclaurin series of sine x is what? So it is okay. An times x to the power n. Actually, it is x minus c to the power n, and from 0 to infinity, but c is just 0. So this is an x to the power n, and from 0 to n. And we computed all these terms. So let me write couple terms, a0 and then a1x, a2x squared, a3x cubed, and so on. A0 was 1. No, a0 was 0. Okay, let's see. A0 is 0. So it is 0, 1, 0, minus 1 over 3 factorial, and so on. So it's like this. 0 plus 1 plus 0 minus x cubed over 3 factorial, because it is 1 over 3 factorial, and then I have x cubed, and then I will have 0, and then I will have x to the power 5 over 5 factorial. It will be again, so the coefficients will go like this: 0, 1, 0, minus 1, 0, 1, 0, minus 1. But you have n factorials in the denominators, so I will have 0 and then minus 1. So x to the power 7 over 7 factorial, and it will go like this. So this is just actually n from 0 to infinity minus 1 to the power n, and then I have x to the power 2n minus 1 divided by 2n minus 1 or plus 1 factorial. So for n equals 0, it is x over 1 factorial. For n equals 1, it is x cubed over 3 factorial. There is a minus sign. For n equals 2, it is x to the power 5 divided by 5 factorial, and so on. So the Taylor series for sine x is this. What is the radius of convergence? Well, you see here, this is not actually a typical power series. Here I have only x odd powers of x. Odd powers of x. Even powers doesn't appear. You can do the following. You know, okay. So I can regard this as my terms, and then again, so we can talk about L, which is limit an plus 1 over an, and this will be just limit. So nth term is the coefficient of nth term is 1 over 2n plus 1. N plus 1 term will be 1 over 2n plus, you plug n plus 1 for n, so you get 2n plus 3 factorial, and then divided by an, 2n plus 1 factorial. So this will be just limit 1 over 2n plus 3 times 2n plus 1 as n goes to infinity. Of course, this is 0. Therefore, r, which is 1 over 0, is infinite. So the Taylor series or Maclaurin series converges for all x. Hence, this series, efendim, n yerine n artı 1 yazıyorum ya, 2n artı 1 o zaman şey olacak. Yani 2n artı 1'de n yerine n artı 1 yazıyorum. 2 tane n artı 1 artı 1. Ha, şunu diyorsun. Özür dilerim. Tamam. Tamam. Tamam. Özür dilerim. Hence converges for all x. Okay? Because radius of convergence is infinite for all x. However, this doesn't show that sine x is equal to this gadget. We will see, soon that we will see that that indeed sine x is equal to this gadget. Okay, but we haven't proved that yet. Okay. But for the time being, let's assume this. If you assume this, then Taylor series or Maclaurin series for cosine x will be something very simple, right? So if I assume this, then so if we assume this, taking derivative of both sides, we get what? Derivative of sine x is just, okay, sine x. I know that if you have a power series, right, equal to some function, then its derivative is just computed again as a power series where you just take term-wise derivative, right? So it's just the derivative of this expression. Derivative of this. Derivative of sine is just cosine x, and derivative of this, well, we stated that the derivative of this is just term-wise differentiation. So I just need to take derivative of this expression. 2n plus 1 comes down, right? When you take the derivative, you decrease the power by 1, so you get x to the power 2n divided by 2n plus 1 factorial. And here 2n plus 1 cancels with the last term of this factorial, so you will get just 2n factorial. So this is just 0 to infinite minus 1 to the power n x to the power 2n divided by 2n factorial. And what is the radius of convergence of this? Well, it is still the same radius. Whatever the radius of convergence of f, the derivative function will have the same radius of convergence. So this is true for all x in R. And soon we will show that sine x is equal to actually this expression. Okay, so that sine x is an analytic function. Okay, in general, a function may not be equal to its Maclaurin series or Taylor series. Okay, even though it is infinitely many differentiable, the two functions might be different. But for sine x, it will be the case, so that they are it's a analytic function. Okay. Hmm. Yeah. Derivative of an analytic function is also analytic. Okay. Let me maybe remind, I mean, give as a remark. So this function f of x, e to the power uh, minus 1 over x, if x is positive and 0 otherwise. This function has a graph like this. Okay, it is 0 everywhere up to 0. It goes like this. You see, when x is approaching to 0, 1 over x approaches to 0, sorry, infinity, but you have a minus sign here. So 1 over this goes to minus infinity as x approaches to 0 from right. If you approach this way, this goes to minus infinity. E to the power minus infinity, of course, will be something like this, right? Right, and goes to infinity, so it will go to 0. So this function has such a graph. And as x goes to infinity, 1 over x goes to 0, e to the power 0 is 1. So this thing is something like this. Okay, here this is 1. And it turns out that you may compute the derivatives of this function. Okay, you may compute the derivatives of this function. This is infinity many times differentiable function. Although it is defined piecewise, it is infinity many times differentiable. And if you compute the derivatives of this, any derivative and derivative at 0, they are all 0. Okay. For example, let's see the first derivative. What is f prime x? Well, if x is positive, somewhere here, then the function is this. So what is the derivative of this? It is just 1 over x squared e to the power minus 1 over x, right? If x is positive. Just derivative of this. If x is negative, then it is again 0, right? On an open interval, so it is 0. We just need to compute the derivative at 0. Okay? Well, what is the derivative at 0? This is just limit as h goes to 0, f of 0 plus h divided by h. But here, what is this? Well, it will depend on whether you are approaching to 0 from left or right. So for this limit to exist, I need to compute both left and right limits. Need to compute left and right limits. So let's do that. Limit as h goes to 0 from right. Of course, here I have f of 0. F of 0 plus h minus f of 0 divided by h. But f of 0 is just 0, right? By definition, f of 0 is 0. So I get just f of 0 plus h divided by h. So I need to compute this f of h divided by h. Well, as h goes from to 0 from right, f of h is what? F of h is this expression. So it is limit as h goes to 0 from right, e to the power uh, this divided by h. Okay, now this is 0 over 0 case, because as h goes to 0, this goes to plus infinity, you have minus sign, it will go to minus infinity, e to the power minus infinity goes to 0. So this is a 0 over 0 case. So what we do, we use L'Hopital's rule. Let's do that. When you take derivative of this, derivative of the numerator, it is 1 over h squared, and then I have this divided by 1. Okay, this didn't work well. Okay, let me do it this way. Oradan çıkmayacak. Şöyle yapayım. Bunu şöyle yazayım. 1 over h over e to the power 1 over h. Now it is infinite over infinite case. I can use L'Hopital's again. So derivative of this is minus 1 over h squared. What about the derivative of this? Minus 1 over h squared times e to the power 1 over h. Minus 1 over h squared cancelled. So this is just limit as h goes to 0 from right. These are cancelled. 1 over e to the power 1 over h. H goes to 0. 1 over h goes to infinite. E to the power infinite, right, is infinite. 1 over infinite is just 0. So right limit is 0. What about the left limit? Limit as h goes to 0 from left, f h over h, right? The this limit as h goes to 0 from left. Well, this is easy. As h goes to 0 from left, f of h is just 0. So this is 0 over h. But 0 over h, as h goes to 0, h is never 0. It is getting closer and closer to 0, but it is never 0. So this is just 0, right? Therefore, this limit is 0. So left and right limits both equal to 0. Hence, limit as h goes to 0, f of h over h exists and equals 0. So f prime 0 exists and equals 0. So derivative exists. But this only shows that first derivative exists. You need to compute all the derivatives. So you have to find a way of computing the derivatives, okay? It's not that easy, but it is, I mean, it's true. So this shows what? This shows what? This function, okay, this f of x is a function which is differentiable infinitely many times, but and its derivative at 0 are all 0. Now, if this function were analytic, so if f were analytic, okay, similarly, one can show that all the derivatives of f at 0 exist and 0. Okay, hence the Taylor series, the Maclaurin series for this function f of x is what? Well, it was this nth derivative at 0 divided by n factorial x to the power n. Well, all these derivatives are 0. Therefore, this is just 0. Okay? Well, the Maclaurin series of the function is just 0 because all these coefficients are 0. But this function is not 0, right? This function is not 0. It is 0 maybe for negative x values, but not 0 for positive x values. So there is no interval like this about 0, so that this function is equal to its Maclaurin series, because this function is positive for all positive x values. However, its Maclaurin series is identically 0. Okay? Therefore, this function cannot be analytic. Okay? So this means what? Since f of x is positive for all x greater than 0, f of x cannot be analytic at x equals 0. Because if it were analytic at 0, then in a neighborhood containing 0, f and its Maclaurin series should coincide. However, Maclaurin series is always 0 and f is not always 0. Therefore, f is not equal to its Maclaurin series near 0. Therefore, it is not analytic at 0. Okay? Hence, f of x is not an analytic function. This is maybe just a single example, but it turns out that actually most most of the differentiable functions, they are not analytic. Okay, but the ones we are familiar with, sine x, cosine x, logarithms, exponentials, polynomials, they are all analytic. But in the space of all functions, all differentiable functions, they represent a very small portion. Okay, so that all the rest, they are not analytic. Okay. Okay, now this is just a side remark. Uh, waves, I will show that sine x is analytic, therefore cosine x is analytic. Uh, there are, let's see some more examples of analytic functions. More examples of analytic functions. Okay. Well, we know that this is analytic and it's equal to x to the power n divided by n factorial, right? For all x in R, so radius of convergence is R. And we know this from the theory of differential equations, which you don't know yet, actually. You will see it in differential equations course. But using Taylor's theorem, we can also show that this is the case, okay? However, once we assume this, we can find uh, analytic functions using this. How? For example, just replace x by minus x to get what? E to the power minus x minus x to the power n divided by n factorial. So this is just minus 1 to the power n x to the power n divided by n factorial. Okay, this is true again for all x in R. And using this, I can write this cosine hyperbolic x. It is this gadget, right? Right. Definition of cosine hyperbolic is this. Well, this is just So this is 1 over 2 times e to the power x. It is x to the power n divided by n factorial plus e to the power minus x is just this. Okay. So this is just 0 to infinity 1 over 2 times 1 and then minus 1 to the power n x to the power n divided by n factorial, right? The coefficients are all 1 here, minus 1 to the power n. So I have this. This means what? If n is odd, then this is minus 1, so 1 plus minus 1 is 0. For if n is even, then it is plus 1, so it is just 2. So you get 1. So this is just equal to the following. This is just x to the power 2n. Odd terms cancels out. I have only even terms, 2n factorial, and from 0 to infinity, right? Only the even terms survive. So this is cosine hyperbolic x. And again, this is valid for all x. What about sine hyperbolic x? Okay, sine hyperbolic x. Well, this is just the derivative of cosine hyperbolic x. So if cosine hyperbolic is equal to this one, sine hyperbolic x is the derivative of this. And what is the derivative of this? Derivative. Okay. Well, you just take derivative term-wise. So this is 0 to infinity 2n times x to the power 2n minus 1 divided by 2n factorial. 2n's are cancelled. So I have 0 to infinity x to the power okay, 2n minus bir dakika şöyle yazalım. Bunun birkaç terimini yazalım. 0 koyduğumuzda when n equals 0 I have x to the power 0 which is 1 and then x squared over 2 factorial plus x to the 4 over 4 factorial and so on, right? So when you take derivative you get 0 plus 2x, so it becomes x 4, so this is x cubed over 3 factorial and then x to the 5 over 5 factorial and so on. So when you take derivative you get just okay 2n plus 1 divided by 2n plus 1 factorial, right? When n equals 0 you get x, when n equals 1 you get x cubed and so on. So sine hyperbolic x is this. Sorusu olan var mı? Hı. Bunlara niye hyperbolik function mı deniyor? İyi soru. Yani belki şundan olabilir. Sin x and cosine x yani tam şeyini bilmiyorum ama onlar yani cosine x'in grafiği şöyle bir şey. Sin x'in grafiği böyle bir şey, değil mi? Böyle bir şey. Yani sonsuza gidiyor bunlar. Sinüs ve kosinüs gibi değil. Onlar hani bounded, eksi 1 ile 1 arasında kalıyor. Bir yerde işte o tür şeylere eliptik deniyor. Bunlar sonsuza gittiği için, sonsuza giden kolları olduğu için o yüzden hyperbolik denmiş olabilir. Yani hyperbolik değil mi? Şurada hyperbola hani hatırlarsanız değil mi? Y eşittir 1 bölü x gibi. Muhtemelen yani öyle bir isimlendirme olabilir. Evet. Efendim? Ne olmuş oluyor? Hı hı. Evet, sonsuzda gitmiyor onlar ama bunlar gidiyorlar. O yüzden hani ona hyperbolik denmiş olabilir. Ama tam tarihsel şeyini bilmiyorum işin açıkçası. Okay, now another example. Find Maclaurin series for uh, e to the power minus x squared over 3. B is sine x squared over x. C sine squared x. Okay, now well, we know that e to the power t is this, right? So let's start from this one. From 0 to infinity, x, okay, just t to the power n over n factorial. And here t is any real number. T can be anything. So I can just let t to be minus x squared over 3. Okay, then e to the power this is just minus x squared over 3 to the power n over n factorial. So this is just minus 1 to the power n, x to the power 2n divided by 3 to the power n times n factorial. And here what is x? X is anything, okay? Because, you know, whatever you put x here, you get some t, and I know that the series is convergent. Sine x squared over x, well, sine t is just minus 1 to the power n, t to the power 2n plus 1 divided by 2n plus 1 factorial n from 0 to infinite, right? So it is like t and then t cubed over 3 factorial, t to the power 5 over 5 factorial, goes like this, plus minus plus minus. You have odd powers of t divided by the factorial. Now what is x squared? And this is true again for any t. T can be anything. So just let t equals x squared. Then sine x squared is what? You just let t equals x squared. So you get 0 to infinity minus 1 to the power n x squared to the power 2n plus 1. So x to the power 4n plus 2, right? You just have you have x squared to the power 2n plus 1. So 2 times 2n plus 1 is just 4n plus 2 divided by 2n plus 1 factorial. And what is x? X can be again anything. Tamam mı? Yani t yerine x kare yazıyorum. Bu formülde t yerine x kare yazıyorum. X karenin 2n artı birinci kuvveti. İsterseniz onu daha açık mı yazayım? Şöyle yazayım. x karenin 2n artı birinci kuvveti. But this is equal to minus 1 to the power n, x to the power 4n plus 2 divided by 2n plus 1 factorial, and x is any real number. So sine x squared over x is what? Well, I divide everything by x, okay? Of course, here I shouldn't let x equal 0. Otherwise, this is undefined. But you just divide by x. So when you divide by x, you just get 4n plus 1, 2n plus 1 cube, factorial, sorry. Part C, sine squared x. Well, what is this? This is sine x times sine x, but you know, if you start with the Taylor series for sine x and multiply it with itself, okay, you get Cauchy product, you get another power series, but you know, it doesn't look very handy. There is a trick. Sine squared x is just 1 minus cosine 2x over 2, right? So I can just use this. Cosine t, I know that this is just minus 1 to the power n, t to the power 2n divided by 2n factorial, n from 0 to infinity, and this is true for all t. So just let t equals 2x, then cosine 2x is just 0 to infinity minus 1 to the power 2n, 2x to the power 2n divided by 2n factorial. So this is just minus 1 to the power n, 4x squared, yok şöyle, pardon yanlış oldu. Karesini alırsak 4x karenin, yani şöyle 4 üzeri n, x üzeri 2n, okay, divided by 2n factorial. And again, x is any real number. Because t is any real number, therefore x is any real number. Hence, sine squared x, which is 1 minus cosine 2x divided by 2, is what? This is just 1 over 2 minus 1 over 2 times this. So you get minus 1 to the power n, 4 to the power n, x to the power 2n, 2 times 2n factorial, right? I have this 1 over 2. İsterseniz bunu şöyle de yapabilirsiniz. Bu eksiği içeri de atabilirsiniz. Yani 1 bölü 2 artı n sıfırdan sonsuza eksi 1 üzeri n artı 1, 4 üzeri n, x üzeri 2n, 2 tane 2n factorial. X is any real number. Okay. Another example. Find the Taylor series, not Maclaurin this time, for ln x in powers of x minus 2. Okay. Okay. Well, we showed already that we know that ln 1 plus t was this, right? It was t minus t squared over 2 plus t cubed over 3, just 3 minus t to the 4 over 4, and it's like this. Bunu nerede yaptık? Ben size hemen bulayım. Yani epey oldu tabii bunu yapalı ama. Şurada. Tamam. Ln 1 artı x. Değil mi? Buydu. Eksi 1 üzeri n bölü n x üzeri n. Dolayısıyla ne eşittir? İşte birden başlıyor. Bir dakika. Şurada eksi 1 mi olması lazım? Evet. N eksi 1 var. Onu yanlış yazmışım değil mi? Şurada dikkat ederseniz n eksi 1 şöyle olacak. Tamam. Okey. Yani ilk terim artı sonra eksi artı eksi artı eksi gidiyor. Okay. So I have this. I need to write ln x in powers of x minus 2. So here t was how much? T was less than 1 in absolute value, right? Çünkü 1 bölü 1 eksi t ile başlamıştık. So this was valid for t less than 1. So let t equals x minus 2, then uh, yok şöyle yapalım. Özür dilerim. Özür dilerim. Okay, let's do it this way. Then ln x. I wanna write ln x, right? I can write this way. This is 2 plus x minus 2. Okay. This is ln 2 times 1 plus x minus 2 over 2. Okay. Now logarithm decomposes like this. Logarithm of 2 times logarithm 1 plus x minus 2 over 2, right? I can write it this way. And here now let t equals x minus 2 over 2. 1 plus t, okay? 1 plus t. So ln x is just şurada. Yani x yerine x bölü 2 in star diyeyim. Star bu. Star. Okay. Here you write x minus 2 over 2. So you will get what? ln 2 plus ln 1 plus t. 1 plus t. So it is t minus t squared over 2 plus t cubed over 3 minus t to the 4 over 4 t to the power 5 over 5 goes like this. So this is just ln 2 plus t x minus 2 over 2 minus x minus 2 squared divided by 2 squared. I have extra 2, 2 times 2 to the power 2, plus x minus 2 cubed over 3 times 2 to the power 3, x minus 2 to the 4, 4 times 2 to the power 4, and so on. So this is the Taylor series of ln x in powers of x minus 2. And here t was less than 1 for x minus 2 over 2 less than 1, right? This is t. This is if and only if x minus 2 is less than 2. So the radius of convergence of this power series is 2 units. Okay, 2 units. Radius of convergence is like this. Okay, from 0 to 4. Okay, now let's have a break.